to bridge difference between northern and southern hemisphere number of observations. And the other one is to train young scientists from undeveloped countries through stays in developed countries. And that's a very important thing, I think, and it's the only way to transfer knowledge, and maybe it's the only way to make this world a better world by transferring knowledge and bridging or decreasing the gap between developed and developed countries. So I would like to say this because I think that's very important to me. So thank you again very much. And,
thank you, Vanda.
Yeah.
So just to return very briefly to Vanda's last point, I do have some literature about the Pogo and its capacity building program. Unfortunately, I left them in Vanda's office. Before I leave the university, I will give them to Vanda, and maybe she will pass them around. Because importantly, beginning around about this year, some of our programs are going to be open not just to students from developing countries, but also to developed countries. So, in fact, this year we selected one Portuguese person, and that one first accepted the position for training, but then subsequently was able to get a permanent job, so she stopped. So I will give the literature to Vanda, and maybe she will, if any of you are interested in it, you please see her. So today I want to give a rather general talk about ocean color, and sufficiently general that I hope there'll be something of interest for everybody. So the color of the sea is something that has fascinated people since recorded history. In classical times, you see many references to the color of the ocean, and somehow has captured the imagination of everybody. If you take a ship to different places at different times and you photograph the water, as you can see, and as we know from everyday experience, you will see many different colors of the ocean. And sailors for hundreds of years have known that these differences in the color of the water can provide valuable information for fishermen. And one group of sailors who was that has been particularly interested in implications of ocean color were the captains of the ships looking for whales, especially in the Southern Ocean. And one prominent one is an Englishman, William Scoresby, whose father was also a whaling captain. Scoresby became very, very rich to the point where he was able to retire in his 40s, and he became a gentleman scientist and became a fellow of the Royal Society. He had over 60 publications, including some with famous scientists such as Joule, of the Joule of energy, so to speak. So he was an important observer, and he wrote a book about his experiences. And this book was basic information for people who were looking at either for the whales, either from the point of view of making money from them or from the point of view of studying them. And one person who was engaged to study the whales and their food was Alistair Hardy. I don't know if many of you have heard of the continuous plankton record heard of that? Continuous plankton recorder. This is a program that is still running. He established this in the 1930s, and the program is still running. And earlier in his career, he was employed as a scientist on an expedition to the Southern Ocean to study the relationship between whales and their food. And I'm sure that he would have been aware of Scoresby's work. When he came back from the Southern Ocean, he took a job in the English Department of Fisheries. And he developed a project of using these very small planes to fly over the sea around southwest England with the objective of looking for shoals of pelagic fish, herring and mackerel. So could he survey the area and find the shoals of fish using these small planes? So he proceeded to try this work, and it was a total failure from the point of view of finding or monitoring the shoals. On the other hand, he was a very gifted observer, and by the way, he made almost all the paintings that you will see in this talk from time to time. So he wrote, as you can see at the bottom, we passed over a sharp line separating the green water of the English Channel from the deep blue water of the Atlantic. So he observed this, and he made drawings by hand, and you can still find these drawings in his book, The Open Sea. And he wrote in this book, which is he published later in his career, The Open Sea. I very much recommend it if you've not seen it. He speculated, if these color changes can be correctly interpreted, we may, in the future, find aircraft being used to make rapid survey of surface conditions in relation to fisheries. So this was his speculation and forward-looking view in a book that was published, I think, 1953. So, of course, in the interim, things have changed much faster than he could have imagined, because, in fact, we make survey not just using aircraft, but using instruments on satellites in Earth orbit, and we make use of the information not just for fisheries, but for a number of other things. And these are some of the things I would like to talk to you about. So the point is, we can draw conclusions from these differential coloring of the water. And in particular, we find that the colors contain information about the marine microflora, as we all know as the phytoplankton, which, although on an individual basis are invisible to the naked eye, collectively their impact on the color of the water is sufficiently strong that it can be measured from space. So the phytoplankton have some important and highly relevant properties in this context. First, they are single-celled organisms, as we know, and in the size range from less than 1 micron to about 250 microns. They're green plants, means they contain chlorophyll, and their metabolism is photosynthesis. They're mostly confined to the surface layer, but you can find them everywhere around the world, often in very high concentrations. And in fact, over most of the world's ocean, they are the single most important factor by far that controls the color of the water. And because they make photosynthesis, they are consumers of carbon dioxide, so very important in the context of climate change. And the collective metabolism is very, very large. It's order 50 gigatons of carbon per year. The other thing is that they're slightly heavy with respect to water. So they have a tendency to sink, and that sinking tendency depends, of course, on their cell size. Now, if we think about the ocean as a physical system or a thermodynamic system, we would characterize it as being an open system and a dissipative system. And therefore, its activity can be sustained only through a regular supply of energy. And of course, the energy supply in this case is coming from the sun. And before we can have any useful benefit from the energy supply of the sun, it has to be coupled in some way to the ecosystem itself. So the interface or the coupling between the energy supply and the elements of the ecosystem is the pigment contained in phytoplankton. It's a transducer or an interface, however you want to look at it. And then, because this light can be captured in the marine microflora, we have the situation that the ocean, in the ocean we can talk about biogeochemistry, whereas otherwise we would talk only about geochemistry. And the light will enter the ocean, will be in some cases have some interaction with the phytoplankton cells, and eventually some of the light may escape from the surface of the ocean back into the atmosphere and possibly beyond the atmosphere to space. So the light that escapes back from the ocean is the basis of the ocean color signal that we are going to study and try to decode for its whatever information it might have for us about the ecosystem and about the biogeochemical cycles that operate therein. So these are some of the points we're going to mention. There are applications in physical oceanography. There are applications in ocean biogeochemistry. There are applications in applied ecology of the pelagic system, and they have implications for marine resources. Now, we have light coming into the ocean from the sun, and that light may be either absorbed by phytoplankton pigments, that's one possibility. It may be absorbed by the water itself, or it may be scattered. You know, there is, these phytoplankton are in size, are of a similar size to the wavelength of the light that is coming in the light in the visible range, in other words. And so we have this phenomenon called scattering, where the stream of photons coming from the sun, individual photon track may be changed in its direction. So if it's coming in this direction, it may end up going over there. This it would be due to something called scattering. So those are the principal things that can happen through the photons here. And the other point is that we may have, as well as interaction with the phytoplankton, we may have interaction with sediment, with dissolved organic matter in the water. And if the water is shallow enough, there may be some reflection from the bottom. If you have a white sand in a shallow, say, reef area, then the optical signal leaving the water will contain some information about this bottom. But that's only when the water is shallow. So these are the things that can affect the light that escapes from the sea and may be measured by a sensor on a spacecraft. We would like to quantify the effect of constituents in the water on the ocean color signal. How does that work? So here, for example, is an image of a phytoplankton bloom. Here. This is southwest England, and this is northern France. And so you see here the water is a milky blue color. This picture in color is as close to the colors as we can make it with the equipment, as close to the colors that you would see with your naked eye in this picture. It's called a pseudo true color. So you see here the effect of a phytoplankton bloom. If you look up in that channel at the top of the picture, you can see the red color, which is caused by sediments coming out of the Bristol Channel. So this is a true color picture. I stress that because subsequently we're going to look at a different kind of color picture. So here, for example, this is now a color-coded picture where the color scale in this case represents a concentration of chlorophyll. So this is a more typical ocean color image than the one in the previous slide, because shows the distribution of chlorophyll. Of course, the chlorophyll is contained in the plankton. Distribution of chlorophyll at a fairly large geographical scale. This happens to be the east coast of Canada. And when we analyze the ocean color signal, the first and the principal thing that we are trying to learn is the concentration of chlorophyll. That's the principal product of ocean color research. So ocean color, or if you give it a more fancy name, is visible spectral radiometry of the ocean. So ocean color is the common name. Is a method to produce these images showing the large-scale distribution of chlorophyll concentration. So most people feel that the images are very beautiful, and they are, but it's best to keep in mind always that to produce them, we have to use very strict radiative transfer theory. It's a problem in optical physics. So one thing that we can do with the chlorophyll field is to compute the prime production. So does everybody know what the prime production means in this context? It's the rate of change of the rate of growth of the phytoplankton through photosynthesis. So how do we do it? We have to know the light energy at the top of the atmosphere. That's quite easy to calculate because it's an astronomical calculation. You know, it's something that changes with the day and changes with the depends on which latitude you happen to be in. Then we have to have a model called atmospheric transmission. How much light is lost in the atmosphere, and then we get the surface irradiance, and because the production is going on throughout the euphotic zone, we have to calculate the irradiance at different depths, and this we do by knowing the profile of chlorophyll in the water, typical profile, and the surface chlorophyll, and allows us to estimate the irradiance at depth. And we rely also on a light penetration model for that. Now, once we know the irradiance and we know the chlorophyll biomass, then we can apply so-called photosynthesis light model. That's a model of the photosynthetic response of the chlorophyll to particular irradiance. And in this model, we need to assign two parameters we can tell you about. Then we calculate at that point it becomes easy to calculate the prime production at depth. So this is a procedure that's in standard use now. And tell you a little bit more about the parameters involved. So what do we need? First of all, we require the so-called initial slope of the photosynthesis light curve. It means the rate of change of photosynthesis with light at very low light levels. So at low light levels, this relationship is almost linear. So this linear slope of this curve is the first thing we need. So although the curve starts out being linear, after some time it saturates, actually the curve itself is a hyperbola, so it will saturate. There's an asymptote which is called the assimilation number. And so these are the two principal photosynthesis parameters we need. We need to know the absorption coefficient of phytoplankton per unit chlorophyll. That's called the specific absorption coefficient. And we need to know the ratio of carbon to chlorophyll in phytoplankton. Now, of these things we need to know, the one for which we have the least information is the carbon to chlorophyll ratio. So one of the recent developments in the field has been to try to estimate this from ocean color. Need the carbon to chlorophyll ratio to convert between a field of chlorophyll that we might get from satellite imagery and a field of carbon that you might get from a numerical model. So in one of the methods that we use for calculating prime production. When it comes to the assignment of parameters, we base the assignment also on ocean color. So the requirement is that we have an archive of data from the field, including the chlorophyll concentration and the temperature at the station concerned, but also the parameters of a photosynthesis light curve that we can measure on the ship. So we have such an archive. There's maybe 1,000 entries in it that includes estimates of photosynthesis parameters as well as estimates from satellite, estimates of in situ chlorophyll and temperature. So what do? We often need to make these calculations on particular pixels, means particular elements of the image. And here is an image of sea surface temperature. This is an image of chlorophyll. So using those two values, we look in the archive to see what information we have about photosynthesis parameters in this region of the chlorophyll and temperature space. So this is one basic method that we use to get the parameters of, to calculate photosynthesis. Now, coming back now to this problem of the carbon to chlorophyll ratio, the reason that this is a difficult problem is that if you, in the field, you take a plankton sample and you, for a particular value of chlorophyll, which would be here, if you look at the corresponding value of carbon, that carbon, as well as being carbon from phytoplankton, will include carbon from detritus and from bacteria, from many sources, as you can imagine. So the method that has been adopted in our work on this is to, whereas we could have made a regression through all the data there, we have made what's called a quartile regression, where we look at the minimum possible line, it's the red one, that would relate the carbon and chlorophyll. And the argument is the minimal possible line will have the least contamination of other kinds of carbon in the estimate of phytoplankton carbon. And in fact, we've been able to do this where the phytoplankton are partitioned into major taxa. So this gives us a way, you see the red line top left here, it allows us to calculate some regression curve relating phytoplankton carbon and HPLC chlorophyll. So now we've applied those data to produce this set of pictures. First one is the chlorophyll field, and then the next one is the estimate of particulate organic carbon. That would be the black regression through the data. Then an estimate of phytoplankton carbon. That would be based on the red line regression. Carbon to chlorophyll ratio. Assimilation number, as I showed you from the growth rate, the carbon-specific growth rate, which is a quantity that people were struggling to get by remote sensing for many years. Now, I want to switch the topic a little more towards physics. When the light is absorbed by phytoplankton, only a very small fraction actually is used for photosynthesis. Most of it is dissipated as heat. And in fact, even the part that goes into photosynthesis eventually will be dissipated as heat of respiration. So, but we can separate the immediate energy going into photosynthesis and the part that is going to be just heating the water. So you can see two different cases here. A cartoon of a place where the chlorophyll concentration is rather low. And there we will have low growth rate. The photic zone will tend to be deep, and the physical mixed layer will tend to be deep also. On the other hand, on the right side, this is now a cartoon of a place where the chlorophyll concentration is much higher. The photic zone will tend to be shallow because, of course, this K, by the way, is the vertical attenuation for light in K that we all know about in the ocean. Will be more shallow because the K will be much higher. Mixed tend to be less deep, and we tend to get higher growth rates. So this shows two somewhat extreme cases. And in fact, if you look here, this is on this axis is plotted the mixed layer depth multiplied by the attenuation coefficient. So this is a dimensionless quantity that appears in the theory of mixed layer growth. So this is the growth rate per day, and you can see that when the highest growth rates occur when this dimensionless product is less. Now, physically, does it matter? So, I would like to persuade you that the presence of chlorophyll in the water changes the seasonal development of the mixed layer, and in particular the seasonal development of mixed layer temperature. So the top picture is for the Labrador Sea, that's off eastern Canada, and the bottom picture is for the Grand Banks of Newfoundland, where all the Portuguese used to go for salt cod. So this is the seasonal cycle, and you can see in the top one that at the peak, the temperature in the water is 1.5 degrees higher than it would be if there were no chlorophyll. And of course, in reality, seasonally, we have change in the concentration of chlorophyll throughout the year. For example, we have the phenomenon of the spring bloom, which would be around here in this case. And it means that as the chlorophyll concentration increases for biological reasons, because of this relation I showed between the mixed layer depth and mixed layer an optical attenuation in the mixed layer, that there is a feedback that is helping to promote this temperature difference. On the Grand Bank, you can see that it's of order 2.5 degrees. So these are differences that even now physicists don't necessarily take into account. And it's possible to take them into account because using the ocean color remote sensing, we can have very complete information about the seasonal development of chlorophyll. Now, am I taking too long, Brenda, or how are we doing? What time is it? 10 past. All right, thank you. Now, beyond the absolute biomass of chlorophyll, we can aspire, we can hope to learn something about either the kinds of phytoplankton present or the cell size of the phytoplankton present. So this is another area of research in ocean color. Notice that the presence of phytoplankton modifies the optical environment in which the phytoplankton live. So this picture here is a spectrum, or a series of spectra, of the distribution of light at the base of the photic zone. And it's different depending on the concentration of chlorophyll. So at very low chlorophyll concentrations, the light at the base of the photic zone will be blue. And at very high concentrations, the light at the base of the mixed layer, of the photic layer, will be green. And you have variations in between. So the optical environment of these cells, whose mode of nutrition is optical, fundamentally, is modified by their own presence. So it provides a possible mechanism for a species succession and for maintenance of biodiversity, because the different taxonomic groups have slight differences in the absorption spectra. So if you make the appropriate calculations based on the spectral models like this, then you can show very nicely the possibility for maintenance of biodiversity and the succession of the species throughout the year. The community structure, or what's called these days the phytoplankton functional types, partitioned into major taxa, also has biogeochemical implications, because different taxonomic groups of phytoplankton have different impacts on the major chemical cycles in the ocean. So, for example, a conventional model of the ecosystem with a nutrient pool, phytoplankton, zooplankton, and detrital pool, like this famous one by Michael Fashion, does not take into account any differences or any qualitative differences in the, shall we say, the inhabitants of the phytoplankton pool. It's just one box. Whereas models of the present day take into account the differences between organisms such as diatoms who impact on the silicon cycle, calcifying organisms such as coccolithophores that are vulnerable to ocean acidification, organisms that have an influence in the sulfur cycle, and nitrogen-fixing organisms, for example. So these are all quite different biogeochemically, and you will find the models now that take all this into account. And it allows one to address questions such as those related to the carbon cycle. Is the prime production increasing or not? Is the production of dimethyl sulfide increasing or decreasing? What is the effect of on the cloud condensation nuclei? And so on. So when we address these questions, we should pay attention to the phytoplankton functional types. And you will get, rather than the one pool of phytoplankton, as I showed in the fashion model, you get this case where the phytoplankton pool is separated into half a dozen or so different boxes. Now, what can the ocean color tell us about phytoplankton community structure? We have to look at the absorption spectra and look for small differences in the spectra that we can exploit to determine the presence of one functional type or another. Here are estimates based on the model of Sathyendranath of the probability that individual pixels in this image were dominated by diatoms. So this one is for the spring, and this is for the summer. And you see strong representation of diatoms in the spring, but much less so in the summer. Now, who cares about that? Here is a picture from a publication about the Benguela system of southern Africa. This shows in conditions where the water column is stable, the favored phytoplankton are flagellates, whereas during turbulent periods, the favored phytoplankton are diatoms. And the food chains associated with flagellates and diatoms are sufficiently different that the small pelagic fish that prosper under the two conditions are different. Either we get sardines or we get anchovies. And they don't have the same market value. So it's easy to see that if the Canadian model were applied in the South African system, that maybe some forecasting ability would be possible. And a further recent development in this field is that we can recover information about the cell size of phytoplankton. It's quite theoretical so I won't show the equations. But the point is that once the cell size has been recovered, it allows us to use a variety of allometric models to calculate things about the ecosystem, including potential fish yields. I think I have to pass some of these. Now, another topic is this of stewardship of the ocean. Is stewardship okay, or is it a difficult word? Anyway, it's taking care of the ocean, at the level of national politics or even international politics. You know, are we preserving the ocean as we should? So there is a global agreement now that when we manage ocean resources, we should do it with the so-called ecosystem-based approach. I think this is now a declaration of the United Nations. So that means that one should preserve health and vigor and resilience of the ocean. It's very easy to agree to, but very, very difficult to implement, because they are not scientific words. Health is, and vigor is, you know, they're not things that we can quantify. So one alternative way is to look for ecosystem indicators that tell us something that is accepted scientifically about the ecosystem. And if you have a few of these indicators that taken together, they are informative about the state of the ecosystem, and that we can apply those indicators and a time series to see if things are changing. Right? So here is how you make a time series. You get a series of images that might occupy, for example, a full year. You put them in order. And for the area of interest, you extract a property, in this case, chlorophyll. And then you do this for every image in the series, and you're able to draw this seasonal variation. And of course, in temperate latitudes, this series, or this time series, is very highly structured and dominated, for example, by the spring bloom. Now, just to briefly, I mentioned one application in fisheries. This is survival of a gadoid fish, the haddock, in eastern Canada. And these are the anomalies in timing of the spring bloom. So it means that when the numbers are negative, it means that the spring bloom was late compared with the long time average. And when the numbers are positive, means the spring bloom was early with respect to the long-term average. So I think it's easy to see that when the spring bloom is early in a particular year, we have the best chance of larval survival and recruitment to the fishery. So this is one example of an application of an ecosystem indicator. So we can do, I showed the time series for a particular place. You can look at the thing on a global scale. Do we have time, Vanda?
Yeah.
It only lasts for a minute, this movie. If I can make it start, I don't know. Is there a mouse? Is there a mouse here? So this is animation from NASA of the seasonal development of phytoplankton over a period of a few years. So this is obviously winter. Now you see the spring bloom coming. And it will go like that through many years. So is a big interest in marine science now in calculating and interpreting the various aspects of the seasonality in the plankton. And the fancy name for this is phenology, means the study of life cycle events. So, I think it will stop just now. Huh? You think it's escape will do it? Escape will take it from here. So, there are many indicators. I showed one about the timing of the spring bloom. There are many indicators that we can get from ocean color, including things about the prime reduction and the photosynthesis parameters, carbon cycle properties, and so on. So there's a big scope for constructing indicators that may be useful in decision making about management of marine resources. And we've had many applications of these things from harvest fisheries or in fisheries management where one would use, for example, the information I showed about the haddock, one would use that in taking into consideration quota setting for haddock. You can use it to calculate carrying capacity for aquaculture and so on. Now one of the more trendy things is the so-called ecosystem services. Many of them can be calculated from ocean color data. And ocean color data, by the way, or remotely sensed data are particularly suitable because they have very good resolution on the ground. They have very frequent remeasuring, and there are many reasons why they are very suitable for this kind of work. So, let's finish with that. Ocean color, or this remote sensing of ocean color, provides the only window we have and that we ever will have in the foreseeable future, window into the pelagic ecosystem on synaptic scales. It's an integrating discipline in that it uses a lot of information about phytoplankton taxonomy and physiology, as well as requiring strong support from marine optics. And can be applied to problems of social interest. Of course, it's not a universal panacea because there are limitations, but it is extremely versatile and it is cost effective. But there remain many stimulating problems to study. And when we study those outstanding problems, we'll make the best progress when we combine the data on ocean color with data from other sources, either in situ or other kinds of remote sensing and also modeling. This is still a rather young field. Technology is still improving. Its use in ecosystem-based management remains to be developed further, and it perhaps is a useful vehicle to draw into the field of oceanography new students who are essential to fill the worldwide scale shortage of relevant expertise. So this is what I wanted to say. say, and thank you for your attention.
Thank you for your interesting talk, Trevor. I didn't understand just a small thing. When you presented those graphs of Eastern Canada with the vertical distribution of temperature, you had higher temperatures on the surface
Yes,
because of higher concentration of chlorine.
yes.
But there was like a mirror in the lower depth.
Ah.
There was a lower in
Yeah,
temperature.
yeah.
Well, what's that?
It's just a balance because
It's a transfer.
yeah, if you trap more heat in the surface layer, it's not passing below into the, so there's a starvation, if you like. Once you put the chlorophyll near the surface, there will be a starvation of heating in the lower layer that may have been there when there was no chlorophyll, but as soon as you put the chlorophyll, change the distribution of heating in favor of the surface. So, just a simple balance.
Thank you.
Yeah. Yes, please.
Could you give us your view of what can be done in terms of secondary production?
Secondary production is very difficult, and I mean there's a small number of papers in this direction, but you have to try. You need to try to find something to in the secondary producers or their activity that has an optical signal. So that's the trick. I mean, we're very fortunate in a way that we can learn as much as we can in the autotrophic part. But for the moment, I think there are no major breakthroughs for secondary production. If I may digress a little bit though, one thing that I didn't have a slide for here is recently working with a biochemist in Canada, we have started to work on the quantification of fatty acids in the phytoplankton with a view to, in fact we have one publication now where we try to calculate the supply of fatty acids on a world scale versus the demand, the nutritional demand that we have for fatty acids. It's not secondary production, I know, but it's a topic that is another new one. I'm afraid I didn't get a slide about it. Yes. The picture I showed didn't take into account those differences. It simply said, ignoring those differences, it said, will the growth rate tend to be higher or lower if the layer is shallow or less shallow? And the point is that if you consider that surface layer as being mixed, then we calculate something called the average light level in that layer for the day. And so that light level will tend to be higher when the layer is more shallow. And the reason is that the deeper the layer, the bigger the share of the available photons will be captured by the water itself. You know, when you have photon stream on the water, then there is a partition, there's competition between phytoplankton and water for share of the photons. and that partition is optimal in a more shallow layer. Is it okay? Yes, sir.
Thank you for your presentation.
Sir.
I'm a normal oceanographer, so I start before the remote sensing observations. So I remember to do all the coast of Africa and Portugal, making lines and with a scale of blue and green
Yes.
scale. We just measure
Yeah.
and we were able to plot the regions with more phytoplankton,
Yeah.
less phytoplankton.
Yeah.
And at the same time, we also just made an inventory of the birds
Right.
out there,
Yeah.
and it was coincidental,
Yeah.
those things.
Yeah.
And now it's so much things, so much more. It's fantastic.
But
And it's 50 years.
but don't think that this color scale don't think it's finished, because in the continuous plankton recorder they still match against the color scale. That's still going on. And then in the literature in the last less than 10 years, there's been arguments about whether on a global scale chlorophyll is decreasing or increasing or staying the same over 100 years. And that led to quite a strong debate in a recent symposium in Plymouth, which was in honor of the 80th year of the continuous plankton recorder. And there was a Dutchman speaking who very much favored this the Forel scale, and he used that kind of information to counter the arguments that the chlorophyll was going down on a 50 to 100 year timescale. So I think there is still room for that kind of observation.
Fantastic.
Yeah.
So just another compliment.
Yes.
You made the forecasting of states.
Yes.
So you went forecasting for the future
Yes.
occurrences.
Yes.
So I think of any possibility to make it backwards, to combine color with oceanography.
Yeah. I don't know about paleo on that longer scale, but let's keep the time scale to 100 years. The phenology or timing of the spring bloom depends on the establishment of a stable surface layer. Right? So it's possible that you can look backwards in the physical data to find, to quantify this part of the cycle, and that therefore looking backwards to try to say something about the phytoplankton phenology.
Or the ecosystem.
Or the ecosystem itself, yeah.
Thank you.
Because there's a nice, somebody has come with a very nice indicator, a very simple one, for you're familiar with the spare drop hypothesis about spring bloom. So how to find, in the context of spare drop, a very nice indicator. And these people have said there is a flux of heat across the sea surface all the time, and that in the spring the sign will change. Sign of this surface heat flux will change. And that should be the magic day, that should be the thing we are concentrating on in trying to rationalize the phenology. So I think personally I think it's I wish I did it, but somebody else did it.
Thank you.
Yeah. Okay, I'm sorry I took so long.